Hello, my name is Garnet Caribbean, and this is my solution to question number 5 on the review packet. The question asks us to solve the system where x prime is equal to a of x. A is the matrix 1, 4, 1, 1, and x sub 0 is equal to 1, 2. So, in order to solve a system like this, we'll actually consider a solution format in the form of x is equal to c times e to the rt. In order to evaluate a solution in this form, we'll actually have to check for x prime, because that's the only thing that we're given. So we'll actually take the derivative of this. So x prime is equal to, it would be c, because it's a constant, times e to the rt, the derivative is equal to r e to the rt. And we want this to be equal to a c e to the rt. In order for this to work, we'll actually subtract this from both sides, and we'll get the equation that 0 is equal to a minus r I c e to the rt. Everything here would simplify in the way that we wanted to. Everything makes sense except for this I. This I is actually the diagonal unit matrix, which allows us to actually subtract this constant r by this a value. Because of this, in order for us to get a solution in this format, and a solution that's not the trivial solution, meaning that c does not equal 0, we have to set this equal to this. So in order to do that, because 0 is a value, we actually have to check the magnitude of this, found by the determinant. So the determinant of a minus ri is equal to 0. This is the equation we have to solve for r in order to find the eigenvalues of this equation, of this system. So let's solve this. So a minus ri will be equal to, a is equal to 1, 4, 1, 1. If we subtract r from the two diagonals, this one, these two, we will get that this is equal to 1 minus r times 4 times 1 times 1 minus r. And if we take the determinant of this matrix, we're checking to see that the determinant equals to 0. Don't forget that. I'll write it after I write the terms out. But in order to take the determinant, we'll multiply the diagonals and subtract this diagonal by this one. So negative 1 minus r squared, 1 minus r times 1 minus r, subtracted by 1 times 4. And this is equal to 0. So let's factor. Well, let's distribute. We get r squared minus r plus 1. And then that is subtracted by a negative 4 is equal to 0. And this will translate to, combined like terms, we get r squared minus 2r minus 3 is equal to 0. This can be factored out. What multiplies to negative 3 and adds to negative 2? The answer is r minus 3 and r plus 1 is equal to 0. And in order for either of these to be 0, it either has to be 3 or negative 1. So r is equal to, negative 1, 3. Oh, you didn't see that last one. But r is equal to negative 1, 3. These are actually the eigenvalues that we will use to find the eigenvectors. So this solves for the eigenvalues. This is the eigenvalue. Or each of these are individually eigenvalues. So if we look at the first one, we can utilize this to find a solution to this, this system of equations right here. How do we do that? Well, let's plug in r back into this equation right here. We get a minus a negative 1r is equal to, if we plug it into here, we get 1 plus 1, because it's a negative 1, 4, 1, and then 1 plus 1. To check, to utilize this to find, actually let me simplify this more, 2, 4, 1, 2. I just added the ones together. To utilize this to find our actual x, we have to look at it in the idea that a times c is equal to 0. Right? This a, which is what we solved for right here, this a times this c is equal to 0. That's what I meant. I'm sorry. So we check to see that 0 is equal to a minus ri times c, which goes to, in this case, 0 is equal to this matrix times c, because we're looking at a vector c and there's only 2 rows on this, we're actually looking at the vectors c1, c2. And we evaluate this for the constants. You'll notice that when we multiply c1 and c2 in, this one has a c1, this one has a c1, this one has a c2, this one has a c2. These rows are actually translations of each other. This top system and this bottom system are exactly the same. This is just the bottom system multiplied by 2. So if we multiply these c1s and c2s in, we only have to look at one of the rows. We'll look at the bottom row, just to make it easier since we don't have to simplify as much. So if we multiply these in, we'll get that 0 is equal to c1 plus 2c2. If we subtract 2c2 on both sides, we'll get that c1 is equal to negative 2c2. And since we have some sort of relationship between c1 and c2, we can actually grab the original c value and make it, if we plug in negative 2c2 into where c1 is, we can actually put this in terms of a single variable. And if we pull the variable out, we'll get that c times negative 2, 1 is our solution for that. I took away the 2 because this is an arbitrary constant, and after this part, we won't need to actually label them because there's no different constants anymore. We only have 1. So I pulled it out and made it a c instead. This can be plugged right back into here. Not here, I'm sorry. The original equation that I had labeled for c, and we'll get a solution using this r value. So the solution is equal to c times negative 2, 1 vector times e to the rt, where r is actually equal to negative 1, negative t, because it's negative 1 times t. So this is our first solution. Now we have to do the same exact thing for the second r value. R2 is equal to 3. So you remember the equation was 1 minus r, 4, 1, 1 minus r. So we plug in 3 for r. We will get 1 minus 3, 4, 1, 1 minus 3. And this is equal to negative 2, 4, 1, negative 2. So this is our new matrix. Using the same formula we had before, where 0 is equal to a times c, we can say that 0 is equal to a. In fact, actually, I'll rewrite this to skip a step. This 0 is equal to 0 over 0, because it's the 0 vector. It's equal to a times c, which is still equal to c1, c2. But these are different c1, c2s. This differs from the last question because this is just a new set of arbitrary constants for r equals 3. So, like we saw in the last one, you can actually multiply this bottom equation by negative 2 and get this top equation. So we only have to look at one of them, which makes this a lot faster. So we'll only look at the bottom equation. So if we multiply C1 and C2 into this matrix, we'll get that 0 is equal to C1 minus 2C2. If we add C2 on both sides, we get that C1 is equal to 2C2. And this relationship can be plugged straight back in to the C value in order for us to get this in terms of one constant. And this is the solution that we got. And this can be plugged into the actual solution to the differential equation. And you'll get that the solution is equal to C, excuse me, C times the vector 2, 1, e to the RT. But this R, likewise, from the last one, is equal to the R of the situation. So e to the 3t. So these are two solutions that we got. We can actually, each of these solutions on their own calculates their own set of solutions, but we can combine the solutions in order to get the whole solution to the equation. So the general solution is equal to the combination of the two. x1 is equal to when r equals -1, x2 is equal to when r equals 3. I just put it to show that there are different x values. But if we think about the x equals 1 situation, we get that I'll label it C1 because these constants, this constant and the one from the last R value are actually different. So C1 times -2, 1, e to the -t, plus C2 times 2, 1, e to the 3t. This is the solution to our differential equation. Except we don't know what C1 and C2 are. In order to solve for C1 and C2, what we'll have to do is look back here, and we'll notice that they gave us that x sub 0 is equal to 1, 2. So, because of that initial value that they gave us, this is an IVP problem, initial value problem, we can actually plug the value x sub 0, where t is equal to 0, and 1, 2 into this equation. So if we say that x sub 0 is equal to 1, 2, which is equal to, so if we plug in t0, we'll get, for both of these, we'll actually get e to the 0, which, if you'll know, evaluates to 1. Because of that, this is all multiplied by 1, so we'll only get this term and this term left. So C1 times -2, 1 plus C2 times 2, 1 is equal to this. This is actually just a system of equations where it's -2C1 plus 2C2 equals 1, and 2 is equal to C1 plus C2. So let me write that out as a system. 1 is equal to -2C1 plus 2C2, and 2 is equal to C1 plus C2. So all we have to do is solve for the system equations, and we'll get C1 and C2. If we look at the bottom one, we can see that C1 is -2 here, but C1 here is just 1 C1. If we multiply the bottom one by -2 or +2, we can actually add these two equations together and cancel them out. So we'll do that. So if we multiply the bottom one by +2, we'll get that 4 is equal to 2C1 plus 2C2. We'll add it with the top equation. 1 is equal to -2C1 plus 2C2. These two cancel out. And this evaluates to 5 is equal to 4C2. If we divide by 4, we'll get that C2 is equal to 5 over 4. That's our first solution. For our second solution, we'll have to plug the C2 back into this equation. So we'll get that 2 is equal to C1 plus 5/4. 2 is actually equal to 8/4. If we subtract 8/4 by 5/4, we get 3/4. So C1 is equal to 3/4. So these two are the C values that we got. Now we can plug them back into the general equation that we got and get that x is equal to, plug in for C1, we get 3/4 times, oh yeah, sorry, I was checking my solution to make sure I did this correctly. 3/4 times -2/1 e to the -1t plus 5/4 times 2/1 e to the 3t. And this is the solution to our differential equation. Thank you.